Hello, my name is Abigail Jolley, and I'm a student at Converse College. I'd like to thank South Carolina INBRE and Converse College for their support of my work on the development of first and second generation zero-gel-based and parametric biosensors for the detection of free cholesterol. Biosensors are compact devices that utilize biological mechanisms to recognize target molecules and generate quantitative results. Specifically, parametric biosensors used in this study measure electrical currents generated from electron transfer reactions. The picture on the bottom left shows a schematic of an parametric biosensor in which a sample with many analytes is introduced to a biosensor, but only a specific analyte will interact with the bioreceptor layer to produce a measured signal or current. The picture on the right shows how every injection of an analyte produces a step in a current, which is directly proportional to the analyte concentration. In the development of these sensors, both first and second generation sensors were utilized. A second generation sensor includes a mediator layer, shown in orange, which facilitates the movement of electrons to the platinum surface of the biosensor electrode. A first generation sensor doesn't include this mediator layer. The sensors used in this study were developed using a layer-by-layer approach. The layer shown in green consists of a silane and the enzyme. The silane acts as a scaffold that helps the enzyme to maintain its shape and therefore its function. The layer shown in blue is an outer layer of polyurethane. This layer prevents interfering molecules found in the body, such as acetaminophen, glucose, or uric acid, from being detected by the sensor while still allowing the smaller analyte cholesterol to pass through and be detected. Specifically in this study, when an injection of cholesterol is made, the cholesterol interacts with a cholesterol oxidase enzyme in the silane layer to produce hydrogen peroxide. An applied voltage to the electrode then oxidizes the hydrogen peroxide to produce electrons, which are the measured current. In the development of these sensors, the silane layer was optimized by testing the use of different silanes. Both APTES and PTMS were tested. They are very similar silane molecules that only differ in their side chain. Additionally, the biosensors were tested using an outer coating and without that polyurethane outer coating. You can see in the IT curves below that when an outer coating of polyurethane was used, the background noise of the signals was very much decreased. Additionally, you can see from the pictures below that APTES produces a much cleaner signal than PTMS. From these IT curves, calibration curves were generated to allow for analyzing the different silane layers. The slope of these calibration curves allows us to determine the sensitivity of the sensors. As you can see, PTMS has a higher slope and therefore a better sensitivity. However, PTMS has a larger error. So APTS was used as the enzyme silane layer in this biosensor. Interference studies were also conducted once the biosensors were optimized. In interference studies, the biosensors are prepared as normal, and then interferents are injected, specifically acetaminophen, ascorbic acid, sodium nitrate, oxalic acid, uric acid, and glucose injections were made to the biosensor. The goal is to see very little signal from these interferents and thus we can show that we are blocking these interference from being measured. At the end of the study, injections of cholesterol are made to prove that the cholesterol is being measured and not the interference. We went a step further in our interference studies to improve the sensitivity of these sensors by adding a polyphenol layer. This resulted in the curve seen at the very top of the picture on the left. Since not much can be seen from this picture, on the right there is a zoomed in picture where you can see clearly the steps from the interference as well as from cholesterol. This clearly shows that adding the polyphenol layer was very helpful in minimizing the effect of interfering molecules while maximizing the measurement of cholesterol. In conclusion, first and second generation amperometric biosensors using a layer-by-layer approach can detect free cholesterol at clinically relevant concentrations with adequate sensitivity, reproducibility, and selectivity. The layer-by-layer approach allows for easy modification for blocking of interfering signals. Future studies will examine the efficacy of these sensors in synthetic blood samples. Thank you for your time and attention during my presentation.